Okay, recording is rolling. It is Tuesday, January 31st, and I've got a bunch of demos for you guys today. So a couple of mirror puzzles lined up, and then yeah. So some of these I'm gonna lead through your textbook shoots and stuff. Some I got some slides on a computer. I got some videos queued up for you guys. So let's start with these puzzles. So here's some mirror puzzles from Paul Hewitt. And actually, we've done a couple of these already. So yesterday when we were doing the Kahoot, the puzzles that popped up were this guy here. He's standing in front of a dresser mirror. How much mirror does he actually need to see his full self? If you guys remember, the answer was half. Right? The catch is, yeah, have to position it exactly correctly. But if he's 6 feet tall, he only needs 3 feet of mirror to see his entire self. And that's independent of how close or far away he stands from the mirror surface. That really goes hand in hand with this next question. So if you're holding a handheld mirror in front of you. Okay. Now, assuming it's flat, so if it's a plane mirror, this would be true. Okay. If you hold it further away or closer, how much of yourself do you see? You can try this yourself with that one right there or home, and the answer is the same. So if you hold it further away, you see the same amount of your face. Hold it closer, you see the same proportion of your face. That's the same thing. Okay. But here's the one that we haven't done yet. So the first one. Okay. You zoom in here. It says she's standing 1 meter in front of the mirror. So you guys see that, right? So I got dresser mirror here. She's 1 meter away, so 1 meter. Okay. And she's trying to see this flower on her head, but let's suppose that she can't see the direct reflection of the flower because it's kind of like on the back of her head. Right? If it's drawn exactly like that, but you guys can use your imagination a little bit, right? So the flower's kind of on the back of her head. She can't see it. So instead, now she's going to hold up this handheld mirror, and she's going to see the reflection of the flower. Right? You guys get that? So she's looking in this mirror, see a reflection of this reflection of this flower, right? Okay. And this handheld mirror is a half a meter behind her, behind the back of her head, so behind this flower. Right? So question, how far in the back of the dresser mirror does she see the image of the flower? So if you start at this point and then look back behind, you see a reflection of a flower. I'll give you guys a multiple choice. So give you guys a little time to think about that one. This one ends up being pretty tough for students. Not very many students can figure this one out, but I want you guys to think about that a little bit. One of those four is the answer. While you guys think about it, I'm gonna sketch it up larger to go over the answer. Soft screen here. All right, let's see show of hands what you guys are thinking. How many guys think that going from the mirror surface backward, back into the reflection, how many guys say she sees the image of the flower 1 meter back? So nobody says that. Who says 1.5 meters? So that's got a couple of votes. Who says 2 meters? Okay. Who's got a couple of votes? Who says 3 meters? Okay. Right, so here. If you said 2 meters, you are right. You got it. Okay, you said 2 meters. Okay, and I'll show you guys why. So let's do one step at a time here. So here's the same picture, just blown up a little bit bigger. Okay. Maybe I'll start from the flower. How about that? Let's start from the flower. Now, if you start from the flower, is the flower in this handheld mirror going to appear to be a half a meter behind that mirror? It's going to appear to be like right about here. Okay. You can do like a whole ray diagram with it. I mean, it's a flat plane mirror. Some of those Paul Hewitt did one with like a candle. It's going to appear to be a half of a meter back behind that reflection. It's like equidistant, right? Okay. Now she's trying to see that reflection in the reflection of the dresser mirror. Okay. And this whole distance from here to here, well, that's 2 meters, right? 2.0 meters. Okay. So the reflection of the reflection is going to appear to be 2 meters back. 2.0 meters. Right, so that's one way to think of it. Okay. So this could be 1.5 meters to the stressor mirror, 1.5 meters to the dresser mirror, and then another half meter to the reflection of the reflection. Okay, so the answer is 2 meters. Okay. And there is one more mirrors question, and most students do get this one. Involves this bridge down here. So say there's someone taking a photograph of, oh, it looks like a friend on a bridge, I guess. Okay. And the question is, what is that photograph going to look like? And they've narrowed it down to 2 options. So option A or option B, right? Left or right. Okay. So show of hands, how do you guys think that she takes this picture? It should look like picture A. Who think that? Who says picture B? Okay, yeah. Some of you guys are voting for picture B. Yeah. Okay. And what gives it away? It's like the shadow underneath the bridge, like the underside of the bridge. Okay. So picture A, what they did is they just took the bridge and just like mirrored image it, right? So like put it straight down. But realistically, she was there and she was kind of elevated a little bit. Okay. Maybe she couldn't see the direct underside, but she could see the reflection underneath to like reflect that way. All right, so there you go. Okay, so you guys did good there. That. Another way.
Thanks.
Right, so I'm gonna break out this textbook for some of these. Okay, so you guys do have a pretty good textbook. All right, let's go through some of these other ones, like diffraction and interference, this sort of thing. And starts here with the Huygens principle. Now, Huygens principle is this idea like, oh, whoops, back a little bit. Let's see what I'm reading here. Right, Huygens principle. This idea like if there's like some ripple wave going out, you could treat it as like a bunch of individual points that are each emitting their own ripples individually, and that just aggregate to one like giant ripple wave. Okay? You guys remember a couple weeks back I brought out that ripple tank, right? And I put like different arms in it to oscillate. So there was like a single arm that oscillated, and that would send out just like ripple waves that look like pretty close to circles, right? Right. And then I tried different things too. So there's like a straight wave, right? Those created like a straight wave front. Okay? Actually, that's a good example of Huygens principle right there. Because like the straight wave, if you have like a straight bar like vibrating up down, sending ripples in the water, it's like, well, why are all the ripples like straight? Right? Well, individually, like every single point would want to send out a ripple that's like circular, like emitting from that point. And this is a continuous process. So if you have like a million individual points, right, either on a circular front or on a straight front, right, it's just going to continue that aggregate pattern, right? So a straight wave, the individual points. Like seeing a single point might send out like a circle wave. That they're all lined up straight. It's going to send out like a straight wave, like that. All right, let's look at talk about diffraction here. Right? Oh, whoops. Okay, here they're talking about diffraction. This page here. So there are 3 main categories of like changing waves or bending waves, and we've covered 2 of them: reflection and refraction. So we've done those, but the one I haven't really talked about much yet is this diffraction. So diffraction is like, for example, water ripples might go through like some opening or around a corner, right? So some version of that. Right? Here, look, she set up like a straight wave. Right? So you guys see before it hits all the stuff is just like straight wave, straight wave, straight wave. Right? But then once the ripples leave this individual point, now everything in this from that looks like circle patterns, right? Oh, and that's an example of like Huygens principle, right? Work there. Okay, here's some actual photographs that's happening. And you guys see like if there's like a really tiny pinpoint, right, get these nice circle ripples, right? And then if the opening's really wide, okay, it's kind of circular on the left and the right, but then down the middle is kind of a continuation of a straight wave, right? Okay. And then how exactly will this diffraction work out? Well, it depends. Here, it's like going around a corner or going around an object. How large is the object compared to the wavelength of the waves? Like you guys see this third one, there's a really tiny wavelength and a relatively large object. So, okay, so great like this where like there's this path that like splits, right? Versus if the wavelength is larger in proportion to the object, then it'll like reform pretty well like that. All right. Young's interference experiment. So this is a really famous experiment, the double slit experiment. And I'll tell you guys why it's important, and it's going to show up later in this class too. So what if you have like a card, right, and say we break out a ripple wave machine, we're sending out like ripple waves, right? And we cut like 2 holes in the card, right? Bam, bam, 2 holes, right? Or 2 holes, or 2 holes, right? A little bit different variations on that, right? Well, you guys know that through 1 hole, they would want to, these waves would want to continue according to avoidance principle, just like in the circle pattern, right? But if you've got 2 holes, then it's going to create this interference pattern. That's actually one of my posters. You guys see one of these posters hanging up, shows like an interference pattern. Right? You guys can see like some like straight lines that kind of emerge, right? Right, that's what like an interference pattern would be like on the back wall, right? Got this constructive and destructive interference that periodically oscillates. Now, what is this good for? Well, one thing this is good for is to show evidence that something even is a wave. Because if you try to define like what is a wave versus what is a particle, because there could be like 2 categories of matter, like does it fit into the particle camp or into the wave camp, right? Now that might seem kind of obvious, like, well, is it oscillating or not, right? But there are like boundary cases where it's kind of iffy, and it was debated for hundreds of years. For example, what is light? Is light fundamentally made of particles, or is it fundamentally like some kind of wave? Like Isaac Newton was in the particle camp, called like corpuscles that would be made out of. There are other scientists that know it would be waves. And this experiment seemed to settle the debate that light was in fact made of waves, because they say, oh, well, if you shine a light through a card, you have a couple of slits, then it will create this like interference pattern, right? And that only works with waves, so light must be a wave, right? It seems settled for a long time. Now, enter quantum mechanics, like beginning of the 20th century, the answer actually ends up being a bit more complicated. Light ends up having a dual nature. That's actually true for also electrons or anything that's really tiny, like atomic size. What is particle or wave gets kind of fuzzy. So yeah, anything that small has like a dual nature of both particles and waves. In fact, this double slit experiment specifically was expanded upon with quantum mechanics, and there's like a really weird twist on this that we're going to come back and revisit in May. So in May, when we're talking about quantum mechanics, we'll say, hey, you guys remember that double slit experiment I was talking about? Oh, here's like a really weird twist extension on that. So that's kind of come back in the future. All right, there you go. Take a light, shine through, 2 slits on a card, interference pattern. Okay, there you go. Start talking about. Right here. All right, iridescence. Here we go, iridescence. So you guys know, like if you hold up a CD, right? Like what color is a CD? Okay, well, it's kind of like mirror sort of color, right? But then if you like hold it in light and like turn it, it has like this rainbow effect. Like you see all these different colors. Well, that's not like pigments of light. That's something to do with the like the shape of the surface. Now somewhere else you see this is a lot of like bird wings or butterfly wings. And there's a similar effect over here with like gasoline or thin films, right? Where what the colors that you see aren't because of some kind of pigment that's releasing a wavelength into the world, but instead it has to do with like the shape of the material down at a microscopic level. So let me switch my screen over here. All right, this one. Okay, so there you're looking at like a butterfly wing. The alien is like super shiny like that. It might be an indication there's something kind of odd going on. So like why is this butterfly look all like shiny blue, right? It's not because it's like blue pigment that's absorbing everything except for blue and releasing that back into the world. If you get down at the microscopic level, here's like what a butterfly wing looks like, right? It's not really colored blue at all. It's just like a bunch of ridges that have an order of magnitude that's similar to wavelengths of visible light. Like 1 micrometer, that's like a millionth of a meter, right? Hey, visible light. Here, I got the boundaries for it on this poster right here. Visible light goes from like 380 nanometers, that's like violet, 750 nanometers, which is like red. So like hundreds of nanometers. Ooh, that's like half a micrometer, right? That's like the same order of magnitude. Okay, so whatever light hits the surface, right, because it's shaped like that, right, it'll reflect that color. Like if you took a butterfly wing and you like round it up so it wasn't like shaped like that, like, or if you flattened it out, it would not appear to be that blue color anymore. It wouldn't be all like shiny like that. Same thing with like a compact disc, right? It's got a bunch of little pits in it, right, which contain the information for like maybe like a song track or something. Okay? And then that's why it looks shiny, because down at the microscopic level, it has pits that are about that size. All right, let's do spectroscopy. After that, I'm gonna bring this back over here. Find. Here we go. So I have a few of these spectroscopes. Now these aren't like super high tech. These are pretty cheap ones, but you can kind of get the effect here. I'll pass this one around so you can see, but I've got some more on my demo shelf if you want to get hold of these. If you look through here and you point this at the fluorescent light in the room, it will take this fluorescent light, which is basically white light, pretty close to white light, right? And it'll break it into colors. But that's what white light is, right? It's just opposed to all the colors. So let me go ahead and do that. Pass this around. You guys need to point this. Just look through the eyepiece, look straight at the fluorescent light, and it'll break it into like rainbow colors. Okay? Now, the more high-tech version of this, here's what it looks like. Here's a spectroscope, right? And you could point this at, say, like distant stars, and see what elements the star is made out of. And here's why that would work. Is because every element in the periodic table will actually reflect and absorb different parts of the electromagnetic spectrum. So here's just the visible part. And this picture is showing that the top one is for hydrogen, the middle one is sodium, and the bottom one is mercury, according to the book. You guys see that poster over there on the wall? It says spectral lines. Okay, so I have the first 8 elements there. So hydrogen through oxygen. Okay. And then if there was an astronomer that pointed at a spectroscope at some distant star, that's how they would know, say, what proportion of it is hydrogen versus helium versus like trace elements. And say, oh, there's not very much hydrogen in this one, but there's a high proportion of oxygen. Oh, it must be an old star. It's been going through fusion for a long time. It's probably pretty close to like dying or something. Another thing you can do with this is if you ever read a science article that says like, oh, we discovered a new planet that's somewhere way off in the galaxy, and it's a water-rich planet. Like, how the heck would they ever know that it's a water-rich planet? Well, if they can get starlight going through the atmosphere of the planet, and that atmosphere shows spectral lines that are showing a lot of hydrogen and oxygen, say like in a 2-to-1 ratio, that's how they know that that atmosphere on that planet has a lot of water and vapor in it, right? Oh, hence it would be a water-rich planet. Like, that's how they would know that, right? Another thing you can do with these spectral lines is most galaxies that you look at, let's say, so far away galaxies now, we're talking about outside the Milky Way, actually these spectral lines are shifted, and most of them are shifted, well, to the left on this picture, right? So okay, so stars like mostly hydrogen, but all these lines are like shifted a little bit to the left, right? And then for like Andromeda galaxy, they'd be shifted a little bit to the right, which tells you something about the relative motion of these galaxies. I want to draw this out for you guys. Okay. It's called red shifting and blue shifting. I haven't talked to you guys about red shifting and blue shifting, have I? I don't think so. Okay. Okay. Keep track of what I'm telling each class. Okay. Right, so let me draw some galaxies here. Okay. Let's say this is like us, the Milky Way, huge galaxy, right? Okay, so we're somewhere in there, right? And these astronomers are looking around at different like other galaxies. Let's say they're pointing spectroscopes. Okay? Draw a galaxy here. I'll call this guy Andromeda. Okay? And then let's say this other galaxy could be one of like millions of other galaxies. So just some general galaxy. Okay? Okay. Now, most galaxies that we look at are like red shifted. And that's an indication that they're moving away from us. Right, and I'll show you guys why. This has to do with the Doppler effect, that Doppler shift. Okay. But not Andromeda galaxy. Andromeda galaxy is like blue shifted, which is an indication moving towards us. Because you guys remember from Doppler shift, like if a car goes by on the roads, it's like, meow, right? Well, you can play a similar but a little bit different equation to light. And if something's moving away from us, it's an indication that the light wave is like stretched out. If something's moving towards us, it's an indication that light waves just like bunch together, like decreased frequency and increased frequency. You can say a longer wavelength and a shorter wavelength. Okay. Well, the longer wavelength, that's like closer to the red end of the spectrum. So this is called red shifting. And the shorter wavelengths, well, it's closer to like the blue or the violet end of the spectrum. So this is called blue shifting. Okay. almost everything is redshifted compared to the Milky Way. Right? Andromeda is an exception, which means that Andromeda Galaxy is eventually going to crash into the Milky Way. I mean, like I think a couple billion years from now or something like that. Right? These two are eventually going to collide. Right? But almost everything else is redshifted, which is an indication that it's moving away from us. Right? There's some kind of universal expansion. In fact, the ones that are further away, there's actually even more redshifting. They're moving faster away from us, which is a hint about how the universe expands. It has to do with like this cosmological expansion. So like if you can see all the individual universes, let's say like every end of my fingertips like a galaxy. Okay? They're all moving away from each other uniformly in such a way that there is kind of no center of the universe, or I've heard it said the center of the universe is kind of everywhere all at once. Okay. So the space between all these galaxies is expanding uniformly. And they know that because of this spectrometry and this redshifting. All right. All right, let's switch over and do some video demos. All right, so first one up, let's look at okay, sorry, not that one. That one. Oh, come on here. Let's do a pinhole camera. Right. Just gonna mute this one and narrate it myself. Okay. She has a good explanation for this pinhole camera, but okay. Yeah, you guys see on the chalkboard behind her showing like these spectral lines going straight lines. Okay. So what they eventually do here, I'll just show you guys their experiment here. Okay. So they go into these hotel rooms. I think you're some hotel room in San Francisco. Okay. And they okay, so hanging the sheet on the back wall. Okay, great. Well, I wonder what this is about. Okay. All right. And they cover this window in this black plastic, right, to make the room completely dark. Oh, but well, I would say completely dark, except they cut this 4-centimeter diameter hole in it. Okay, so what's that about? Okay. Okay, so with the slide, okay, so there's the outside world, right? You guys see all the skyscrapers, okay, San Francisco, okay. Oh, you guys remember that sheet they hung up behind? Oh, look at that. Hey, look, it's upside down. You guys see like an upside down picture of the outside San Francisco scene, right? All the skyscrapers are upside down, right? All right, so when you block off all the light except for like one small hole to let the light race in, let's go back to setup beforehand. She's explaining this thing. Right, every ray of light just wants to move in a straight line. So like the top of the building is going to go straight through this hole and go to like the bottom of the room. And anything that's like down on ground level, down on the sidewalks, is going to be just a straight shot up to like the top of the room behind them. Okay, that's why it inverts the image. It's like upside down. Okay. Also, okay, so back to their experiment. Throughout this experiment, they change the size of the hole. See, like they go to 3 centimeters diameter, and later on they go 2 centimeters diameter. And as they make the hole smaller and smaller, there's like a trade-off. So the smaller they make the hole, the sharper the image is going to show up on the back. Ah, look at that. That's a really sharp looking image now, right? All right, 2 centimeters. Okay. The downside is that not as much light is getting in. There you go, 1 centimeter. Right? So to take that picture there, they probably needed a long exposure time. Like they had to like stand there completely still for like a few seconds while enough light was able to enter the camera so they could like get that shot. Right. So again, there's like a trade-off. The larger the hole, the more light information. The smaller the hole, the sharper the image. Okay. Speaking of cameras, this was actually the same principle that some of the first cameras used. Right. So like back in the 19th century when photography was just getting started, basically, if you take this hotel room and just shrink it down to the size of a box you could carry around, that was like the first cameras. They were these pinhole cameras. Right? They would take a pinhole, and then the back of the camera, they had a material that would record the light information that went onto it. So they would expose it for like some time. You guys know a bunch of 19th century photographs of people, like people usually aren't smiling. They're just standing there completely still because, you know, it's kind of hard to like maintain expression and be completely still while that light information is like exposing the photographic film. Right. All right, let's do some video demos from the YouTubes. All right. Let me back up a few here. All right, Pepper's Ghost. There we go. Oh, you guys ever gone over to Disney World, maybe like Haunted Mansion, and it is a common place they'll use this trick you guys are about to see. If you ever see, you know, yeah, especially Disney World, they use all over the place. anything that looks kind of like ghosty, like, oh, I don't think that's really there, but it looks like some kind of ghost just like running across the theme park, right? How do they create that effect? Show you right here.
Today, I'm going to show you how to make the Pepper's Ghost illusion. It's an old special effects technique for creating transparent ghostly images. It works by reflecting the image of a ghost off a clear material such as plexiglass. The ghost is located off to one side where it's out of view. The plexiglass is set at a 45-degree angle to both the audience and the ghost. At this angle, the background remains clearly visible, but the plexiglass also partially reflects an image of the ghost. To the audience, it looks like there's a transparent ghost in the scene in front of them. It's pretty simple. So now I'm going to show you some ways that you can implement this technique. The simplest way to apply it is in photographs and video. Start by setting up your camera on a tripod. Then position your ghost to one side of the camera. The ghost can be a person, a computer monitor, or just a paper cutout. Hold up the plexiglass at a 45-degree angle to the camera and the ghost. The camera should see a faint reflection of the ghost. You may also get reflections of other objects around the ghost. To avoid this, you can set up your ghost in front of a black backdrop. This is a really easy way to make ghost pictures, and it doesn't require any editing software. Creating a Pepper's Ghost illusion for a live audience is a little more difficult. The easiest example is making a ghost appear in a window. First, you need a large sheet of plexiglass. Then you need a way to prop it up behind the window. To do this, I put a table underneath the window, and I added sheets of cardboard to it to make a surface that's level with the windowsill. I propped up the plexiglass in the corner of the window. I also added a small clamp to help hold it in place. Then I positioned the ghost to the side of the window just out of view. You need the room to be dark so that the edges of the plexiglass won't be visible. In this case, you don't need a black backdrop, but you do need to use a flashlight to help illuminate the ghost. The result is a transparent figure in the window that stares at people as they walk by your house.
Yeah, so pretty cool, right? All right. Okay, so this next one I got lined up is on holograms, but I gotta preface that with lasers. Right? So you need lasers to make these holograms that you guys are about to see. So what is laser light? Like how is this different from like regular light? And so okay, so one thing is, I mean, it's a solid color. So I got red light. So the physics term for that would be like monochromatic, right? Mono one chromatic color, so like one color. Right? That's not all. You also need it to be coherent. Right? Now, of course, laser lights, you wouldn't want to like shine this in your eyes because you might like go permanently blind by doing something like that. So don't do that. Right? And so here's here's just regular white light. Now, regular white light, of course, is composed of like all these different colors, all these different wavelengths. So the long ones are like the reds, the medium ones are like the greens, the short ones are like the blues and the violets. Okay? Now, if you can just get one wavelength of color, you're monochromatic. That's not quite a laser yet. That would just be like a red light. So if you have like a red light bulb that just makes the whole room red or something like that, that's what this could be. Just red light. It's all the same wavelength. You need one more thing. You make the light coherent. That means you're going to match crest to crest and trough to trough. Okay? Now, how do you actually like engineer a laser? Right? How is this thing like manufactured? Now that is actually related to there's like a quantum mechanics explanation for this that has to do with like photons of light. Again, it goes back to the idea of like what are photons? Are they particles or waves? Well, it's kind of runs some fuzzy boundaries. So I've seen an explanation for how lasers work. It has to do with like bouncing light back and forth, and then as a matter of statistical probability, the photons are more likely to align like this to make coherent light. So we got monochromatic coherent light that will create like laser light. And you can use that to create, here you go, holograms. It's a hologram. So let's flip back over and let's look at holograms. How do they work?
Holograms are confusing. They're those weird 3D ghost images that appear to follow you as you move, but they're actually completely flat 2D films, and yet they have motion parallax. That is, as you move your gaze, things in the foreground seem to shift faster than things in the background, and they give you a stereoscopic view. That is, you see two different images with each eye, which together create the perception of depth. 3D movies aren't even this 3D. They don't even have motion parallax. And that hologram of Tupac at Coachella, it wasn't even three-dimensional in any way. I digress. So holograms need some really special properties to appear 3D. One is that they show different images depending on where you stand in front of the hologram. This is really unusual. Let's recall that when you look at a regular photograph, it looks the same no matter which way you look at it. What you're seeing when you look at the photo is a white light beam. White light is like a crowd of people. They're walking with different footstep lengths, like the different wavelengths or colors in white light, in every different direction as the light spreads out. That beam reflecting off the photo is like freeze framing the white light crowd. Blue light here, red light there, and it's stagnant. You can't move the crowd around. Blue parts will always be here to the left of those red parts. With a hologram, you can move. It provides that parallax effect. Check it out. This is the setup to make one type of hologram, although the other types are similar. It starts with a laser beam, which is split into two. Then both of the beams go through lenses to make them spread out. One beam, the object beam, bounces off the object you're trying to image and shines onto the holographic film, while the other beam, the reference beam, goes straight there. And then, well, this is why we used lasers. Laser light looks very different from white light. It's all going in the same direction, it all has the same wavelength, and it's coherent, meaning all the light waves are in phase or in unison. This is so key to making holograms. In cases where two coherent laser beams meet, they can create regular striped interference patterns like this. In our case, the reference beam is a coherent beam, though the object beam is not. Still, when they meet, they also create an interference pattern, but a special one that encodes the specific 3D information about the object onto the holographic film. Now, we had a reference beam and an object beam, and together they created an interference pattern. A plus B equals C. What would happen if we took the interference pattern and sent the reference beam in through the back? That's kind of like C minus A. Well, that equals B. And sure enough, with this type of hologram, sending a laser beam in through the back of the film is how you get out the original object beam. That's the same beam that was created when the laser first shined off the object. Since this reproduced beam is a perfect copy of the object beam, you can't tell whether you're looking at the light from the hologram or from the original scene, complete with motion parallax and stereoscopic views. The other cool thing about holograms is that all parts of the hologram carry information about the object. So you could cut a little square of the hologram and you'd still be able to see the entire object in it. You can't do that with a photograph. Deep down though, the holographic film is just a bunch of interference patterns. Up close, the film looks like this, whereas a photographic film just looks like a smaller version of the image. Much less cool.
Gonna skip that one. Come back.
This is the hollow head. Absolutely.
All right, so we got Charlie Chaplin mask. I don't know if you know this guy, he was a famous actor back in the silent film era. But all right, so we got a mask of this guy rotating. Now, this is a pretty powerful illusion, or can be, right? So you guys know how faces are like convex, right? Basically, why not, right? And the inside of a mask should be like concave. But all right, so it's going to go around again. So it looks convex, just like a face, right? And the inside of the mask, even though you know the inside of the mask is concave, it probably also looks convex and looks like it flipped and started rotating the other way, right? Or that's probably what you see. That's what I see, even though obviously we all know how the illusion's working, right? If you don't see the illusion at all, like if you see the concave side of the mask, like, oh yeah, that totally looks concave. Like that doesn't freak me at all. That is a possible warning sign that you might be schizophrenic. So yeah, if you can't see the illusion, then yeah, surprise, you might have schizophrenia. But that probably looks convex, even though it's really concave there. Okay. All right. Now a similar type of illusion. Let me go back to the one I skipped because I've got a sort of spoil this for you guys a little bit. I got this print out that I think I want to give you guys tomorrow. I'm thinking, or at least that's my plans. Right. Ooh, what's the deal with this T-Rex? What? Okay, so somebody's like cutting this guy out and gluing it together somehow. Okay. I'll show you guys the video that's gonna go along with that right there. Let's flip back over. Here. Okay, you can create a pretty cool illusion with the T-Rex that's basically the same thing as this guy.
Hey, go back. There you go. Right. So that's just a single solid piece of paper. Right. Oh yeah. Good. It's not moving at all. But it's been glued together in such a way that doesn't appear to be the case. Right. Again, that looks like a convex face that's on that T-Rex, right? Like it's looking out at you. Right. Now, about halfway through this video, they move the camera enough where it breaks the illusion, kind of like the Charlie Chaplin mask, right? Once it rotated enough, he's like, oh, okay, all right, I see what's going on with the mask. Okay. So same thing here. It's not really a bunch of convex dinosaur faces looking at you. That's actually a bunch of concave faces, right? But your brain doesn't perceive it that way. All right, there you go. There's the illusion broken. So you guys see how you could put this together, right? So when I give you guys the materials eventually, you'll be able to glue it together just like you just saw. Let's see this one more time. Boom. So the face is actually concave, right? You guys see that? It's actually concave. Glue it that way. All right, and we're gonna do one more today. I got a really cool one for you guys from. So this is a femto camera. Okay, it's my femto camera.
Doc Edgerton inspired us with awe and curiosity with this photo of a bullet piercing through an apple, an exposure just a millionth of a second. But now, 50 years later, we can go a million times faster and see the world not at a million or a billion, but 1 trillion frames per second. I present you a new type of photography, femtophotography, a new imaging technique so fast that you can create slow motion videos of light in motion. And with that, we can create cameras that can look around corners beyond line of sight or see inside our body without an X-ray, and really challenge what we mean by a camera. Now, if I take a laser pointer and turn it on and off in 1 trillionth of a second, which is several femtoseconds, I'll create a packet of photons barely a millimeter wide. And that packet of photons, that bullet, will travel at a speed of light, and again, a million times faster than an ordinary bullet. Now, if you take that bullet and take this packet of photons and fire into this bottle, how will those photons shatter into this bottle? How does light look in slow motion? Now, the whole event Now, remember, the whole event is effectively taking place in less than a nanosecond. That's how much time it takes for light to travel. But I'm slowing down in this video by a factor of 10 billion so you can see the light in motion.